Okay, so now what we're going to try and do is formally call this thing the binomial distribution. This is the definition of something that is called the binomial distribution. It looks scary, but we've just done it. So I don't really want you to be memorizing this thing you've got here. I want you to be thinking about how things work. So it says here that you can model a random variable x with a binomial distribution, and I'm going to tell you what this means in a second. B for binomial. N is going to stand for how many times you play the game, and P is the probability of being successful at that game. You are allowed to use the binomial distribution in these 4 different things that you've got here. First of all, if there are a fixed number of trials. So in that previous example, I was playing the game 15 times. I wasn't going to suddenly randomly change it halfway through. It has to be a fixed number of times you're doing the thing. If there are 2 possible outcomes, I either won the game or I lost the game. I wouldn't be able to do it if I was saying it's either a win, a lose, or a draw, or if it was something that was a bit more complicated. There has to be a fixed probability of success. So in the game we just played, every time I played the game, the probability was 0.36. It wasn't allowed to vary during the game. And the trials are independent of each other. That means that every time I play the game, it's like it's got nothing to do with the previous time I've played it or the time I'm going to play it afterwards. That each game does not affect the probability of the other games. So, we're going to talk about this example that we've got here. What are the bits that I want to say? So here what we've got, it says x, and then there's this squiggly line. I'm going to show you how I draw this. So the random variable x, this means is distributed. The b means binomially. The first number will mean how many times you're playing the game. So in the previous example, we played it 15 times. And the p is the probability of the thing happening. So winning the game was 0.36. It's just posh language to try and make something complicated look more neat and written more concisely. Now, I'm going to just quickly do this with the example that we did just before. We were saying, what is the probability that I win the game exactly 5 times? Well, you do n choose r, which is saying n is the number of games. We were interested in it being 5 times. This looks confusing, but it's not confusing. The probability of winning is 0.36, and we wanted to win 5 times. 1 minus p was the 1 minus 0.36, the probability of losing, which was 0.64. And to the power of n minus r, well, we knew it was the power of 10 because we wanted to lose 10 times, which is just 15 times take away 5. It's what we've done. So personally, I don't love this because this puts my students off. This makes people feel like freaked out about what's going on. But you know how to do it because we just did it on the previous page. So don't let this kind of thing get in your way. Don't let this kind of thing make you feel confused by it because we've just done it on the previous page. So we're now going to do this with an example that we've got here. On a table of 8 family members, 6 people are left-handed. Suggest a suitable model for a random variable x, the number of left-handed people in a group of 8, where the probability of being left-handed is 0.1. So the suitable model that we might use here, if we're going to say that the number of people who are left-handed, we're going to say that x is going to be distributed binomially, and we need to fill in 2 things inside the brackets. The first thing is the n, how many people there are. The second thing is the probability that that thing is. So it's going to be 8, and it's going to be 0.1. Then what we're going to do is we're going to actually find the probability that 6 people are left-handed. So I don't really want to think about this thing here. I just want to think about how we did it previously. So I'm trying to now find out the probability that out of the people, 6 of them are successful. In other words, 6 of them have won the game of being left-handed. Well, we know for the first bit we have to do 8 choose 6. We're then going to multiply it by being successful 6 times. So what should I write? 0.1 to the power of 6, and then being unsuccessful, which is 0.9, twice. Notice the 6 and the 2 have to add up to the 8 people that are there. There are 8 people, and we want to find out how many ways are there of choosing 6 of them, because we don't know which are the members of the family that are left-handed. So we're going to calculate this, and we're going to see what the answer might be. So where have I put my calculator? Here. 8 choose 6 times 0.1 to the power of 6 times 0.9 squared. And we get 2.268 times 10 to the power of minus 5, which is 0.0000228. So what does that make us think?
So how did you get 10 to the power of 9?
It just, when I type this on my calculator, it just comes up as that on my calculator. It came up in standard form because it was such a small number. Okay, sometimes people's calculators don't do that. My one just comes up really small. So what was the probability of a family of 8 people and 6 of them being left-handed?
Very, very small.
Insanely small. So now we're going to have a look at part C of the question, which says, suggest why the chosen model may not have been appropriate. So let's have a look. There are 4 things that we need to know about. Well, there are a fixed number of trials. Yeah, but there's 8 people in the family, so that one's fine, that's fixed. There are 2 possible outcomes. You're either left-handed or you're right-handed. Yes, you can be ambidextrous, but for the purpose of this question, there are 2 outcomes. There is a fixed probability of success. Well, yeah, it says that 10% of the population, or 0.1 of people, are left-handed. The trials are independent of each other. You're shaking your head a bit, Andrew. Why not?
Well, because it could be genetical, why someone...
Yeah, it's probably likely. It's seeing as this is such a rare thing to have happened, we think to ourselves, well, it's probably not independent then, is it? It's actually likely that if you've got one left-handed person in the family, maybe the probability is not going to be independent. Maybe if you have a brother or a sister or an auntie or whatever, maybe they also could be left-handed too. So the reason this chosen model may not have been appropriate is left-handedness may not be independent. It may be genetic. And I like what you just said, Sufyan. You said the trials may not be independent. So the trials may not have been independent. We are going to do 3 examples together. That should be quite quick, and then the rest of the lesson is practice, because this is a very, very important topic we're doing here. You're all engaging very well with this so far as well. So just a reminder of what we'd written up here. The example below, success was left-handed. R was the number of successes, so the number of left-handed people. It's not always going to be about a game. It's going to be about lots of different kinds of things as well. So this one doesn't tell you anything about what's going on. I've drawn a diagram to try and help us visualize what's going on. I've said the random variable x, what does this mean again? Is distributed. So the distribution of the probabilities are binomial. There are 12 of them, and the probability is a 6th. I've drawn this. Why do you think I've given this image? How could this image relate to this distribution?
12 dice.
There's 12 dice, and
There's a 6th chance to
there's a
hit.
6th chance of it being a 6. So maybe I could have said, I'm rolling a dice 12 times. What's the probability that I get 2 6s? So the finding out of the probability that I get 2 6s, my first bit, what's my binomial coefficient going to be? 12. Choose 2 multiplied by what? A 6th squared multiplied by 5/6 to the power of 10. The powers have to add up to 12, and that's our number of combinations of how it comes up. So let's get that typed in. Anyone got an answer? 0.2961, and that's to 4 decimal places. I had to round the last bit to get to this. So this is kind of useful. If you were for some reason playing a game with 12 dice and you rolled all 12 of them, there's a 30% chance that 2 of them would have a 6 on it. Now we're going to find out something that feels like a bit different, right? Imagine playing this game, you've got 12 dice, and you want to find out what's the probability when I roll those 12 dice, 9 of them show a 6. Is that going to be likely, unlikely? It's going to be so unlikely that you roll 12 dice and 9 of them have got a 6 on it. So I'm expecting this probability to be really, really low. So the probability that x is equal to 9. Andrew, do you think you could tell me what the whole thing should be? 12, 9, yeah. I know it's not Andrew, everyone's kind of contributing. Sufyan, what's next? 5, 6 to the power of 3. What was this power? A 9. Okay, so can we get that typed in? Anyone got it? I got 0.000123. So I've done that to 4 significant figures. Just a quick shortcut. When it came up on my calculator, it came up like this. Times 10 to the power of minus 5. A little shortcut. When you've got a power of minus 5, there will always be 1, 2, 3, 4, 5 zeros. Okay, so if you ever get it on your calculator like that, you just know it's going to be like that. So basically, it's very, 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 very rare for that kind of thing to happen. Now, the last one we've got is the probability that x is less than or equal to 1. Less than or equal to 1 is going to be a 1 or a 0. So we're going to do a 1, and we're going to add to it a 0. So to get 1, 6, what should the things that we're going to have written here be? 12 choose 1 times by a 6th to the power of 1 times by 5 sixths. Now what is 12 choose 1? You should know that. No, it's not. 12. Because we're saying how many ways are there of getting 1 6 out of 12? There's 12 different ways. And then the next bit, this one I don't even think we need to use the coefficient. We're going to say I get no 6s. What's the probability I get no 6s? 5 6 to the 12. If you wanted to do it the long way, you could have done 12 choose 0 times 1 6th to the power of 0 times 5 6 to the power of 12. But this here is 1 and this here is 1, which is why you can just say you're going to not get a 6 12 times. So that is 12 times a 6.
But it's impossible to get a 0.
Not to get a 0, we're saying getting 0 6s.
Oh, 0.
We're not saying rolling a 0, we're saying getting 0 6s, we're saying getting 1 6. So this first bit I've got is 0.26918 rounded to 5 decimal places. And then I'm just going to do 5 sixths. Oh, I've did 5 sixteenths. No one spotted that. 5 sixths to the power of 12. And that's 0.11216. So if I just add those for the 4 decimal places, I get 0.3813. I'm hoping that's what you got when you did it, even if you did the whole thing on the calculator. So it's quite a strong chance. There's a 38% chance of getting a 1 or a 0. Even more chance than getting exactly 2. What would the probability be of getting 2 or less? Roughly. Yeah?
0.67.
2 or less? No. How would I find out the probability of 2 or less?
Add it.
Add what?
Add the first one.
Add the first one and the last one. So that's like a 30, that's like a 38. It's like a 68% chance of rolling the dice and either getting a 2 or... I didn't hear what you said. Oh, you added them together. I'm sorry, you did get it right. Yeah, that's That's my mistake. So we're going to do 2 worded questions. We're going to do this worded question, and then we're going to do this worded question here. And then you're going to do a bit of practice for the rest of the lesson. So a company claims that a quarter of the bolts sent to them are faulty. To test this claim, the number of faulty bolts in a random sample of 40 is recorded. Give 2 reasons why a binomial distribution may be a suitable model for the number of faulty bolts in the sample. So you've got a choice of the 4 different things you want to pick from here. Anyone got any suggestions about why this could be using a binomial? You can look at the list that came under binomial distribution. There are 2 outcomes. There are 2 outcomes. And the 2 outcomes here are going to either be faulty or not faulty. Good. And there is a fixed probability of success. In this case, our success is being faulty. And that fixed probability is a quarter, because it says a quarter of the bolts are done. The other one we could have mentioned is that there are a fixed number of trials, and we guess that they're going to be independent. But if it's in a factory, they might not be independent. There might be a machine that's broken. So I think these are probably a good one to do. So we're going to now say X is the number of faulty bolts. If you're interested, this thing is called the Test Statistic. And we'll be using that language in the next chapter. But I'm not going to be using it much here. So now I can say that X has a particular distribution. I'm going to write B for binomial. What do you think is going to go inside the brackets?
40 and 10.
40 and not 10, no.
Oh,
And 0.25. I could write a quarter if I wanted to, or I could write 0.25, whichever one you want to do. I don't mind, either of them. You should be familiar that you could see it with a fraction in, or you could see it with a decimal. And we're just going to find out the probability that exactly 10 of them are faulty. What's going to go inside here? 40, 10. Then
0.25.
good. Then
0.75.
good. We're going really fast now. This is good. 40, choose 10. Times 0.25 to the power of 10 times 0.75 to the power of 30. And we get 0.1444 to 4 decimal places. So there's a 14% chance. There's quite a good chance of that happening, right? It's surprising because I would have thought that was going to be higher. If there's 40 of them and a quarter of them are how many we would expect to be faulty, we would predict 10 of them to be faulty. But only 14% chance of that happening.
Right.
But that's because 9 of them being faulty, 8 of them being faulty, 11 of them being faulty, 12 of them being faulty, things nearby to 10 will also have a probability as well. And when you smush all of those probabilities together, it's probably going to get very likely around that area. Okay? One more example and then you're going to try them. Records kept in a hospital show that 3 out of every 10 patients who visit the accident and emergency department have to wait more than 30 minutes. Find, to 3 decimal places, the probability that of the first 12 patients who come to the accident and emergency department, none have to wait longer than 30 minutes and exactly 4 have to wait more than 30 minutes. So we should let X be the number of patients waiting more than 30 minutes. So X is going to be distributed binomially. What should go in my brackets for the binomial bit? 12 and 0.3. The 0.3 comes from this, 3 out of every 10. The first thing it wants me to find is the probability that none of them have to wait longer than 30 minutes. Very good. 0.7 to the power of 12. All 12 of them. There's no point even faffing around with the binomial coefficient. because we know we just want all of them to be failures. We want all of them to be not waiting longer than 30 minutes. So we'll just do 0.7 to the power of 12, 0.01. They wanted it to 3 decimal places, so 0.014 to 3 decimal places. So this is kind of useful, right? If you were managing a hospital and you know that this is the proportion of things that are happening, if you had a day when 12 patients came in and none of them had to wait that long, that's pretty rare for it to happen. Maybe we're starting to improve how well we're keeping patients in our hospital. And then the last one is that exactly 4 have to wait longer than 30 minutes. 12 choose 4. 0.3 for 0.3 to the power of 4 and 0.7 to the power of 8. Make sure the powers add up to 12. So let's just get that in the calculator and then you can try the questions on the next page. I've got 0.231 to 3 decimal places. So there's a 23% chance of exactly 4 having to wait that amount of time. But probably there's going to be a big probability for 3 and 2 as well. So you've got some questions at the bottom of your page that are here. I want you to have a go at these questions, and then we're going to do some from exercise 6B. I'm going to just really quickly do these, just in case you're looking back at this in the future. So probability of x is equal to 2. Okay, that's fine.